This session will introduce how to use Excel to deploy the cross-array experiments and how to calculate the response table and the effect plot. Again, I'm using the nominal best problem as an example to show how do we assign the cross-array design. One inner array for the control factors, another outer array for the noise factors. And this cantilever design has 4 control factors, E, B, H, L, and has 3 noise factors, which is the manufacturing tolerance for the length, the width, and the thickness of the cantilever beam. This is the Excel file where you can see we have arranged the inner array over here to fit 4 control factors in a L9 inner array. And we have 4 noise factors, so we select the L4 and we arrange that in a transpose way to arrange the noise factors over here according to our assignment for L4. So we have 9 different designs, and each design will have 4 samples. In the first samples, we need to consider the design of these 4 control factors under the influence of these 3 noise factors. So in the real case, you should manufacturing the cantilever beam which will reflect this kind of a sampling condition. But in this example, we are using the equation to get the data, and the equation is shown here. K can be estimated by EBH power 3 over 4L to power 3. So in the first sample, we can using the equation to obtain the spring constants. So in the first sample, the equation will be E, which is this value, multiply B. Although B, the nominal value is equal to 4, but in the first sample, this will under the manufacturing errors of this value, which is the lower limit. So we need to plus the error term, and in the actual experiment, this will be 3.97, reflecting the actual value of B under the influence of the noise factor B. And the same thing for H. H, the nominal value in the design is 0.17, but in these samples, this will under the influence of delta H, which is minus 0.003, and this will be to the power of 3, and divided by 4 times of L to the power of 3. L is this cell. Again, we need to consider the influence of the noise factor, which is over here, and the power 3. In this case, we will obtain the estimation of the spring constants for sample 1. You can do the same thing for the rest of the 4 samples and do all the 9 treatment for the inner design. But in the Excel file, if you want to copy the cell into next cell, the equation will be copied in a relative way, since the reference, as you can see from here, if I copy from this cell G5 into H5, all the columns will be relative reference to the next column, which is G to H. So you can see G will become H. All the reference, G will become H and B will become C, which is incorrect for this case. So we need to use the absolute reference in this equation to fix some cell when you copy the equation over. Let's go back to the original equation. This is some small techniques you can learn from the Excel. Since we want to copy the equation into the next columns to simulate different conditions of the noise factors. However, when you copy the control factors into the next columns, you still want the control factor to be the column B through column E. So in the control factors, you need to use absolute reference for that particular cell. So you can place F4 in Excel to toggle between the absolute reference from the fixed column reference or fixed row reference. Here we need to fix the column reference. Therefore, we select the $sign for the column E. Do the same thing for this B5. Since B5 stands for control factor B, so you need to fix the column to B. Again, press F4. And to fix the column, same thing for the control factor C, and the same thing for D5. As to the noise factors, this is fixed at this row. So when you add the noise factors in the equations, you want to fix the noise factor to particular row 1, 2, 3. So in this case, you should use the absolute reference for this noise cell fixed at row 3. Same thing for G1, which is the noise for H, and also for delta H. So using this absolute reference, we will be able to fix the control factors to be this column B to column E. And for the noise factors, we will be able to fix at the row 1 through row 3 when we copy the equation. So when you copy this equation to the next row, as you can see that when I copy to the next columns, the column of control factor will stay at the column B through column E since I fix the column factor. And the same thing, if I copy the equation downward to the next row, and you can double check the equations, when I copy downward, the control factors will automatically use row 5 to row 6 since this will be relative reference. However, for the noise factors, since we fix the row into row 1 through row 3 in the noise part, so when I copy the equation downward, the reference will not change for the noise factor. So we can use the same thing to copy and pass into all the cells and obtain the estimated value for the spring example. Here we use this equation. Okay, in the real experiment, you don't need to worry about that. However, if this is a number can be estimated using a numerical equation, this is some technique in Excel you can use to facilitate your copy of equation over the closed array design. So you can estimate the mean for the first design, same thing for the standard deviation, and the SN ratio will be 10 times log of mean square over standard deviation square. Till you obtain the experimental design, you can have two response tables. The first one is for the mean output, where you use this value to calculate the response table. And for the second response table is for SN ratio, where you use this output SN to compose the response table for the control factors. And this is the corresponding effect plot for the mean output and the SN ratio.